Hello, Professor. This is Kumudini Redicharla, and today I'm presenting my assignment 1, a parallel binary file processing system with resource monitoring. What I've built simulates how real operating systems track memory usage across multiple processes, coordinate them safely, and log system events. So now let me go on and share my screen to demonstrate the work I've done. All right. So the first thing I will be doing is to run the make command inside my directory and now run my program like this. So the first thing my program does is ask the user for file sizes. So I will enter 1 MB, 51 MB, and 100 MB. These are chosen deliberately to show 3 different scenarios. So as you can see, 3 binary files are generated dynamically: worker1.bin, worker2.bin, and worker3.bin, each filled with random data. I am using the open system call with ocreate and otrunc to always start fresh and write to fill them 1 MB at a time. Now the parent process sets up signal handlers using sig action. This is important because it gives us SA sig info, which tells us exactly which worker PID sent the signal. Then it forks 3 child processes in parallel. Each one gets its own binary file to process. So now watch what happens next. Worker 1 processed only 1 MB. It completes cleanly with no memory warning and sends sig user 2 to the parent, which logs its completion. Worker 2 had 51 MB to process. Notice it hits the 50 MB threshold and immediately sends sig user 1 to the parent. The parent catches it and prints the memory warning with the exact worker PID. Then it finishes and sends sig user 2. Worker 3 with 100 MB does the same, exceeds the memory limit, notifies the parent, then completes. You can also see the parallel nature here. Workers don't wait for each other, they run simultaneously. So the memory monitoring works by reading /pros/self/status inside each worker on every chunk read. Specifically, we look at VRMSS, the actual physical RAM the processor is using. Once it crosses 51,200 KB, which is 50 MB, sig user 1 fires, but only once per worker, so we don't flood the parent. Now let's look at the secure processing part. So now when I try to run syslog.log, every event is recorded in syslog.log. So let me show you that now. You can see time-stamped entries for every event. Parent startup, memory warnings with the exact worker PID, and completion messages. What makes this safe is FCNTL file locking. Before any write, the process acquires an FWRLCK write lock. This means even if 2 workers try to log at the exact same time, they take turns instead of corrupting each other's entries. This is the same mechanism real logging systems use. Now let's run an edge case. So for example, I run this again, but now with some boundary values. So I will enter probably 48, 51, and 52 MB. Now watch closely how worker 1 with 48 MB stays just under the threshold and completes cleanly. Workers 2 and 3 with 51 and 52 MB both cross the 50 MB line and trigger warnings. This shows the threshold detection is working precisely at the boundary, not just for obviously large files. Now let's look at each C file. So let me show you the content of part1 file .c, part1 generate.c. So what this does is it creates the binary test files that workers will later read. So there is an open function here that creates a new empty file on disk, like creating a new Word document. srand here, which seeds the random number generator using current time, so every run produces different data. The for loop runs once per MB each time it writes a full 1 MB buffer to the file. And the write function actually pushes the data from memory onto the disk. Finally, the close function saves and closes the file like hitting the Ctrl S button. So now let's look at the content from part2 worker.c file. Part2 worker.c. So here, as you can see, each worker opens its assigned file, reads it chunk by chunk, watches its own memory, and alerts the parent if things get heavy. So we have an open function that opens the file for reading only, like opening a document in read-only mode. And there is a char buffer, which reads the buffer, a small 4 KB reading window. The read function reads the next 4 KB chunk, like turning a page. The accumulator or realloc part, this is what actually builds up memory usage. fopen opens the worker's own memory report. And VMRSS, the specific line we look for is here. And kill sends an alarm signal to the parent, like texting your boss that I'm overwhelmed. And sig user sent 1 make sure we only send the alarm once, not on every single chunk after the threshold. Now let's look at the part3 file, which is this one. So in this file, it sets up the signal handling so that the parent knows when a worker is struggling or done. Think of this like a manager sitting at their desk waiting for calls from employees. So they've set up their phone system to handle 2 types of calls: emergency calls, which is sig user 1, and I am done calls with sig user 2. So it has a struct called sigaction SA. This is the configuration for how to handle incoming signals. And there's sa.sa sigaction handler, kr signal handler, and we have sa sig info, sig empty set, sig action, with sig user 1 being passed and sig user 2 being passed into the function. Now the final part is part 4, so which is part4-log.c. Think of this file like a shared office notebook where multiple people need to write notes. Without rules, 2 people writing at the same time would create a mess. File locking is the rule that says finish your entry before the next person starts. So this safely writes time-stamped log entries to syslog.log, making sure multiple workers don't write at the same time. So there's open function with 6log.log that opens the log file, always adding to the end of it. And struct flock lock, this is the lock configuration like a do not disturb sign. FWRLCK is write log, means I'm writing, nobody else can write right now. FCNTL applies the lock, and so forth. F unlock releases the lock so the next process can write, closes the file cleanly in the end. And we have a main file as well, which basically ties everything together. So it ties everything together, gets user input, generates files, sets up signals, forks workers, and waits for them all to finish. Of course, we do have a make file that basically helps us to to tell the compiler how to put all files together into one executable like this. So so it tells the compiler to put all the 5 files together into one executable. So the challenges I faced, well, the memory never exceeded 50 MB initially for me. When I first wrote the worker to just read the file in 4 KB chunks and discard the data, the memory usage never went above 2 MB. So SIG user 1 was never triggered at all. The assignment itself hinted at this, but actually solving it took some time. So the fix was to accumulate the read data into a growing buffer using realloc, which simulates a real workload holding data in memory. Once I did that, the memory climbed naturally and SIG user 1 fired correctly. And when it comes to self-evaluation, I'd give myself a 9 out of 10. All the core requirements are implemented and working correctly. The file generation, parallel workers, memory monitoring, signal handling, and safe logging all functions as expected and produce the right output. The code is also clean, I believe, and compiles with 0 warnings. So thank you so much for watching my video, and this is the end.